Section 5.3, example 9, using the intermediate value theorem, show that the function f of x is equal to x cubed minus 5x squared plus 3x plus 6 has at least two real zeros between x equals 1 and x equals negative 4. So what we'll start with are those two endpoints. So what intermediate value theorem states is that if we have like a function from A to B, and we have these two values, let me pick a better function. If we have like a function doing this over here, we have A to B. So f of A is over here and f of B is up there. So the function, since it's continuous, it's going to hit each one of these values at least once on its pathway from A to B. So on its pathway from 1 to 4. So let's see, and they want us to show or prove that we have at least two real zeros between 1 and 4. Let's first start with evaluating our functions at 1 and 4. So f of 1. F of 1 is going to be 1 cubed minus 5 times 1 squared plus 3 times 1 plus 6. So we have 1 cubed is 1 minus 5 plus 3 plus 6. So that's negative 4 and negative 1 and 5. So we have the point 1 comma 5. Let's look at the next one. Or let's go over here. Let's say f of 4, the opposite endpoint. So everywhere we see an x, we're going to plug a 4 in. So we have 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. So 4 cubed, that's 64. Minus 5 times 4 squared is 16. Plus 12 plus 6. So 64 plus 12. 64 plus 6 is going to be 70, 82. Minus 5 times 16, 3, 8. So 80, that gives us 2. So when x is 4, y is 2. All right, so far we don't really have much to go off of. If we were to graph these 2 points, we have 1 comma 5, and we have 4 comma 2. So far we know that for sure, because it's continuous, it shows at least each one of these points here. But what we're trying to prove is that it crosses 0 over here. Since we have 1 and 4, why don't we look at all the different values? So 1, or at least full numbers, 2, 3, and 4. So let's try f of 2 next. So f of 2 is equal to 2 cubed minus 5 times 2 squared plus 3 times 2 plus 6. If you want to be a little bit more precise, you could plug this into a calculator, which I should be doing, but I don't know. I'm perfect, aren't I? And plus 6. And we have 8. So 6, 12 plus 8 is 20. Minus, 20, it looks like we got a 0. So we have when x is 2, y is 0, which is our first 0. So they're trying to tell us that there are 2 zeros. Let's give the other one a try. So we have 1, 2, let's look at 3, and then we have 4. See if we see any sort of pattern here. Let's switch this over a little bit more. So f of 3, 3 cubed minus 5 times 3 squared plus 3 times 3 plus 6. 3 cubed is 27 minus 5 times 3 squared is 9 plus 9 plus 6. Let's see, 9 and 6 is 15. So 15 here, that's 242 minus 45, negative 3. This gives us the point when x is 3, y is negative 3. This is actually really important. So let's get like a rough sketch of everything that we've found so far. We have our first point, 1, 5. So when x is 1, y is 5. So that's our first point. F of 2, so when x is 2, y is 0. F of 3, when x is 3, y is negative 3. And lastly, when x is 4, y is 2. All right, so our graph has to do something like this in order for it to hit all of those different points. They wanted us to prove that we have 2 real zeros, and we definitely prove that we have 1 real 0 right here. And using our intermediate value theorem, because we have a continuous function that'll go through those 3 points, it's going to hit every point between these 2 points. So it's going to hit every point between 3 and 4, but it's also going to hit every point between y equals negative 3 and y equals positive 2. One of those points being right here at y equals 0. So we don't know exactly where it is. So we'll just put like a little question mark because we don't know exactly where it is. But based on the intermediate value theorem, we know that it hits a point somewhere between these 2 numbers because it's, well, continuous. And there you go. That's how you could prove that we have 2 rational zeros between 1 and 4. If you have any questions, please feel free to ask. Otherwise, bye.